All right, we're going to move on through unit price with a couple more examples. I know that a lot of you think that, excavation is civil, but I kind of consider excavation the kind of thing that everybody will have to deal with somewhere in one of their projects, as long as you're dealing with an exterior type of project. But we're going to go walk through the three different disciplines with a concrete discipline. We're going to go civil. We're going to go mechanical. That's the next lesson, and the mechanical will be actually a lesson that was recorded in one of the courses. So you might hear other students chiming in, but it won't be you guys, obviously. And then same thing with the electrical. Those instructors are not available right at this time. One of them is actually still deployed, and as a result, we're going to use their pre-recorded lessons that they taught during the course. But we're going to talk in concrete. Let's talk a little bit about concrete. And all I'm trying to do is demonstrate how unit price works, and it's the same methodology with every single section. We're just looking at one section. We're looking at the O3 section. Okay, and the same objectives we saw before. For all unit price lessons, we're going to focus on using a real no-kidding design. And this is where usually some of the programmers will come back to me and say, I don't need to know this stuff. And my answer is, maybe you don't. Somebody in your squadron does. Because if you're doing change orders, if you're doing negotiations with contractors, if you're dealing with Sabre, or if you're dealing in those sections, you got to know how to do this stuff. So we're going to identify and quantify based upon those final designs, whatever those designs are, whether it be Sabre and you're sketching on the back of an envelope, or whether it be a formal A&E addendum that's coming out for a change order, or whether it be the actual full design that you're going to be negotiating with an 8A contractor. You're going to have those requirements that come out of that. And you want to demonstrate the limit to that based upon the cost that you have and the type of cost estimate you're doing. Now, concrete is probably the most extensively used construction material in the world, as it says here. I will tell you that the electrical folks usually end up getting involved with some concrete, so do the mechanical folks. If you're putting in an HVAC pad, you're putting in a concrete slab underneath that. If you're putting in you go out to the switchgear yard, there's concrete all over the place out there. It's a fundamental element, construction material. And the interesting thing is that we've only been using it for about 150 years. So it really has taken over the construction business. Ready mix is typically what you will see on a project site. That's when you bring in the great big concrete truck that's revolving and it dumps it out through the chute and all that kind of stuff. That's coming from a concrete plant. That's normally how we use them in construction projects. There is a common occurrence if you have a remote site, or if you've got a site that's got a lot of work going on at that particular site, you might set up a field batch plant. Like on runways, you might see a field batch plant. Again, large remote sites. It takes a lot of planning to put one of those things together, but it can be less expensive long term. And we're just seeing some experimentation with using 3D printers. I think that's more for the cool factor right now. I don't know that we're at the point yet where that would become something that's really economically viable. But nonetheless, concrete is a material like the plastics they use in 3D printers, and as a result, it is something that could lend itself eventually to that. All right, the way you estimate concrete is in cubic yards, just as we did with the excavation, cubic yards, and you have to know that conversion. Just get it in your head and stick with it, because in the U.S., that's how we operate. We do with cubic feet and converting into cubic yards. I know overseas, you'll deal with cubic meters, and I doubt that we're going to be measuring things in centimeters, but nonetheless, you need to know how to convert those things around as well. There's all kinds of things that are measured in concrete. Typically, concrete is measured in volume. Unlike steel, which is typically measured in tons, concrete is typically measured in volume. And I will tell you, this is the trick with concrete. Concrete is very inexpensive. That's why it's such a widely used material. Concrete, if you're able to pour something in with little or no formwork, you're talking about something extraordinarily cheap compared to wood and steel and other types of materials. The most expensive part of concrete, the most time-consuming part of concrete, by far in both directions, is the formwork. because you spend all this time getting the formwork just right and getting the base and all that cleaned off and everything's all set up, and then you spend a day boring and you're done. It's the formwork is the thing that gets you. So the three things that you estimate for concrete in the unit price world is you price the formwork, you price the reinforcement, and you price the actual placement, which includes both the mix and the placement. Now, I have seen other estimators break these two out, so you buy the concrete and you buy the installation. You have those two separately because while the amount of concrete in a beam and a slab are the same, the placement is different. And so it may make sense to break those out. You can do that, but I'm just going to demonstrate it with the 3 steps, okay? Because RS means we'll let you do it either way. So we're going to price the formwork, we're going to price the reinforcement, and then we're going to price the placement. So we're going to take a look both with talking about it, and we're also going to use an example. So to estimate the formwork, you've got to first identify the type of member that you're doing, because how you place formwork around a beam or a column is different than how you do a slab or a footing. You also price the type of material. Normally, on most small jobs, you're going to see wood wood formwork. And it's typically specialized. I mean, they paint it and they put a special coating on the top of it, but they'll put up plywood for a wall, or they'll put up some boards like 2x12s or something for the footings, or whatever they might be doing, slabs. In that case, the question is, how many times are you going to use that? Because of that wood, if it's made out of wood, it's going to wear out fairly quickly. There are plastic and metal formwork. I keep switching those two. There are plastic and metal formworks. Those things are meant to be reused over and over and over again. You'll find those typically in contractors that do a lot of work of the same type over and over again. Like, for example, special pavements. You might see, if you're doing drives and curbs and stuff like that, there's all kinds of specialized machines and formwork that goes along with that. Then you got to think about the special considerations, because these are not in your standard pricing. These are additionally priced. So you're going to have to go through the whole cost analysis, and then you go to the next section and look for all the adds. And adds would be keyways. A keyway is when you're going to stop one section of concrete and another section of concrete starts, and you want to cut a little, almost a mortise joint, so that the two can fit together and they don't move. They're actually acting as one section. If you're doing an elevated placement, which means you have to have a concrete pump and all that other kind of stuff, not just the formwork is going to be an issue, but also the pumping and the handling of that concrete up to that level. Dowels, liners, archways, or other architectural features and things like that are all going to be considerations that you need to get in to consider in there. Now, with formwork, there's a unit of measure you will find in the RS means, and that formwork unit of measure is SFCA, which is square foot contact area. What that means is the amount of area that actually touches the concrete. You're going to count that square footage. Now, you might come in with a regular 2x12 and actually place a piece of concrete at 10 inches, which means either you bury the 2x12, or less likely you're going to try to measure it exactly 2 inches below the edge. So you might have more square footage of formwork, but they are only counting the contact area. So let's do an example. And this is kind of a simple example, but there's a little bit, because geometry comes into this, folks, there's a little bit of a nuance that you got to follow here. All right, so if you need to stop the video and calculate things out for yourself so that you can keep up, do so. Because typically in class, when I go through this example, 85, 95% of the folks are got it, move on. But then a couple of folks are going, wait a minute, and they're lost. If you're still trying to keep up with how I calculate the geometries, then you're not following everything I say thereafter. So hit the pause button. That's what it's all about. So what we're going to do is find the cost for formwork for putting this footing in here, right here. So we're going to put this footing in, and we're going to put formwork around it. And it's for a stem wall for this building, and it goes in this direction. So the black line is the stem wall of this building. And if you can see the light blue line, okay, that is the interior and exterior of this footing that we're putting in. Now the building's dimensions to the exterior wall, so we're all the way out to that exterior wall that you see right there, is 100 feet wide and 140 feet wide. Now this is where the geometry problem comes in, folks, because we've got to figure out the geometrics of the footing, not that exterior wall. And what we're going to do is place formwork for a continuous wall, so it's all the way around there, all the way around. We're going to pour this all in one day. All right, so that you might say, could we do that? Well, I've done plenty of concrete, folks. I used to work for a soil and materials testing firm, and yes, I did probably tens of thousands of cubic yards of concrete while I was working there. And I will tell you that, can you do this all in one pour? If you had all your ducts lined up, yeah, you could. Yeah, you could. It's possible. And we're going to use one-use forms. So we're going to put those forms in, cut them just to the right size, and then that's it. We're done. We're going to walk away. So first thing we have to do is figure out how many linear feet of formwork we're going to do. And then we're going to multiply times the height to come up with a square foot contact area, right? So we got to figure out how many linear feet. And we've got the inside of the footing, and then we've got the outside of the footing. Now, for the inside of the footing, you've got to take away 2 feet from each dimension. All right, so why we got to do that? Well, here's the exterior of the wall, and we know it's 100, and we know it's 140. We got to take away 2 feet to come up with that dimension right there. So on this dimension, instead of 140, we're taking away 2 feet here and 2 feet here, so that's 136. And from this dimension, we're taking away from 2 feet here and 2 feet there, that's 196, right? So the interior perimeter is 2 times 136, this one and this one, and then 2 times 96. So 464 linear feet of that formwork. On the exterior, we've got to add a foot to each end of the dimension. Why? Because here's the exterior of the wall. We're going to add another foot to go out that direction. So we've got 140. We're going to add 1 here, and we're going to add 1 down there. That's 142. We got 100. We're going to add 1 here, and we're going to add 1 there. That's 102. Okay, so 102, 102, 2 times 102, and 142, 142, 2 times 142. The exterior perimeter, 488 linear feet. Now, I went through that geometry in greater detail simply because we're going to reuse it on a couple more slides, and I want to make sure that you kind of capture that. I don't want you to lose how that geometry looks, because when we get to the reinforcement and we get to the placement, we're going to look at that again. So that's the total number of linear feet of footing that, formwork that I need to place. So I've got to place formwork on the outside, I've got to place formwork on the inside. The total linear feet is going to be that. So there's the total linear feet, right? Now we're going to place a 1 continuous pour, no joints, end forms, keyways. That would mean, when I say 1 continuous pour, that means I don't need joints, I don't need end forms, I don't need keyways. We're just going to start this thing and work our way around and place it. Those things would have to be priced separately. So the square foot contact area. We know what the linear feet is, both inside and outside, but we know the depth is 1 foot, right? So 1 foot times those lengths tells me what the square footage is. So 1 foot times 952 linear feet gives me 952 square feet. All right, so now we know the square foot contact area. Let's go to the RS means, and like I said, I'm not going to give you the scans. We're just going to, because quite frankly, folks, if you get into the scans, as I said before, if you get into the scans, you're going to find pages and pages and pages of options. And you're going to be at a loss as to which one to choose. So I've basically kind of narrowed things down so you can see a usable list of things to then apply to our assignments and to our examples. Of course, if you get into the RS means, you'll get a lot of shopping to do, essentially. You can spend a lot of time in there shopping for the right line item. So what we're doing is forms in place. This is 0311. So this section is concrete. This is structural cast in place, concrete, and we're in forms in place. That's 0.45. Okay, in place means it's the installed cost. They're going to hand form these things as opposed to having some sort of factory form that's set up in there. Okay, so we've got continuous wall, continuous wall footings, one use. So this is the section we're in. We're not in spread footings. We know what spread footings are. Those are under columns. So we're going to go down here. We want one use. Yes, that's the one we're looking for. We're just customizing these things and then walking away. So it looks like that is the line item first thing right up there. Point to point out. I can do 380 linear feet, or I'm sorry, square foot contact area a day. So right now we know we're at around the 900 and something, 952 range. We're looking at probably close to 3 days to put together these forms. And our plan is to pour the concrete all in 1 day. So you can see right now how much time it takes to put together those forms. That has also got a production rate, foot stomp production rate of 0.084 square feet, 1 hour per 0.084 square feet. 1 hour of your crew times, which tells me I've got a number of people on that crew to come up with that time. Now my price, I'm going to use the total column for the majority of the course. We're going to use the total column, so I'm going to use $13.75. So my total cost is $13.75 per square foot contact area. I know the square foot contact area. I can tell you what the price of the total forms for all the forms. I take $13.75 times 952. It comes to $13,090. $13,090. And here's the interesting thing, just again, to show you the dynamics of what the cost is for form work. If I was to take that 380 and multiply it or divide it into that square foot contact area, it would tell me it would be 2.5 days to install the footing alone. So that's typical. I've seen that on project sites. That will take you quite a bit of time just to install the footing around this little small building. So we've got the formwork placed. Now I need to put some reinforcement in there. And that depends on what the reinforcement type is. It's typically taken off by linear feet of your reinforcement, although it's often priced by the weight. So you're going to have to do some sort of conversion, and I'm going to show you that. It might be in hundredweight, which would become, and that's designated by CWT, but it's every 100 pounds is hundredweight. And often it's done in tons. And remember, we use US tons, not other types of tons, not metric tons, not imperial tons. We use the US 2,000 tons. 2,000 pounds is a ton. For larger projects, it's typically cut pre-purchased and bundled and tied and sent to you by specs. For very small projects, you might be doing some hand bending on the site. And that's typically more expensive. It also causes more waste. And if you're in the RS means, you're probably going to look for that additive line item for adjusting these prices, because RS means will typically presume that you're going to get the more economical version. So and by the way, on your homework, you'll use welded wire mesh. It's a type of reinforcement. It's just a different type of reinforcement. So let's talk about what a welded wire mesh looks like. They'll usually give it a designation. And this is a code. This code tells me what the size of the wires are and then what the size of the grid is. It's commonly used in slabs and sidewalks. You'll see it in sidewalks and things like that. What this is the longitudinal wire. So if you're going in one dimension, the one that's the longest is typically the first number. The second number is the transverse wires. And you'll see it'll have a long rectangle. You'll want to place it lengthwise in whatever your design is for. Then these represent the diameters, the size number 8 wire and the size number 12 wire. Now in my head, I don't automatically know what all these diameters are, but we shall see in a couple slides that they're standard diameters across the United States. So what we're going to do is we're going to determine the cost for reinforcement in the footing. Now we're going to use rebar in this example, but welded wire mesh is just another type of reinforcement and another type of a table, and I'll show you that when we go look at the homework. Now the configuration of this thing is that there's going to be 4 bars, and I give you the description here that what we're going to have is they're going to be basically every 6 inches inside the, or every 12 inches inside the footing itself. This is evenly spaced within the footing. So 4 bars in the longitudinal direction, and then in the transverse direction, all right, every 12 inches, starting 6 inches in from the inside wall, or the inside edge of the footing. All right, so let's think of that one through. Again, the geometry is going to come into play here. So we got longitudinal bars are number 5 bars, and they run the entire length of the footing. Now, the civils out there, especially the concrete people like me, know that there's some sort of cover requirement, depending upon what's outside and whether it's in contact with soil or the environment and things like that. There's a cover requirement, which means we can't go all the way to the very edge. But in this example, we're not going to worry about cover. Okay, so I'm not making you think through that stuff. We're not going to go down that road. We're just going to price it for the entire length. So we know the entire length of the footing in this direction, all the way to the outside edge, is 142 feet. If that doesn't make sense to you, go back a couple of slides and watch where we talk about how we come up with the geometry. And the entire length of this one from the outside is 102 feet. So we know that those bars are running 142 and 102. The transverse tie bars are number 4s. They are 2 feet long, and they begin from 6 inches in from either out of the outside edges. So 6 inches in, they're 2 feet long. And they go, 6 inches in from this edge right here, and they run every foot thereafter. Now, I want you to remember the inside edge, the inside dimension of this is 96. And the inside dimension of this is 136. Again, if that doesn't make sense to you, go back a couple of slides where we talked about the geometry of this, and you'll see where we calculate out the inside length is 96 and 136. So I want you to imagine from here, this little dotted line right here, all the way to the other dotted line on the other side is 96 and 136. And essentially we got 6 inches here, then 6 inches to the gap in the middle there, and then 6 inches to there, and then 6 inches. Basically you have 1 rebar every foot of that 96 dimension here, and a rebar every foot of that 136 dimension there. The reason I say that is because we're going to count these guys up. And rather than sit down with a dimension drawing and go 1, 2, 3, 4, I'm going to do it by an equation. Because I know I have 1 rebar every foot on the inside dimension there. So all I need to know is the inside dimension. I know how many rebars I have, right? So let's take a look at this. Total length of the number 5 bars, all right? I've got 4 bars going this way, then I got 4 bars going that way, all right? So that's 2 times the 102. And then I got 4 bars going this way, and 4 bars going that way. That's 2 times the 142, So we got 142, 142, 102, 102, and each one of them are 4 bars. So we multiply that out. I can tell you I've got 1,952 feet of number 5 bars. So That one probably didn't cause a lot of people a lot of conniptions. If it did, stop, go back and think it over again. Think through the geometry. You count them up. You figure out how many bars are and see how that goes. Again, they go the entire length, so I know that the length here is 142 to the outside edges, 102 to the outside edges. I got 4 here, 4 there, 4 there, 4 there. Count them up. Now, let's talk about the transverse bars. We got number 4s. And I got from the inside edge of this footing. All right, so I'm just talking about the inside of the edge of this footing to the inside edge of the bottom footing is in this direction, it's 136. Again, go back a couple of slides if that didn't make sense as far as the geometry. From the inside edge here all the way to the inside edge over there is 96, and I got 1 rebar every foot. Well then, 96 divided by 1 rebar per foot, I know how many feet, how many bars I've got essentially. So 96 bars. The first one, 96 bars on the bottom length because I've got 2 of them, right? One here, one here. That's a total of 192 bars. Then I've got these 2 lengths over here, 136 each. And 1 bar every foot is going to give me 136 divided by those number of bars. I can multiply times 2. I come up with a whole total number of bars of 272 bars. So the total length of number 4s, I've got 2 feet each. 192, 272 times 2 gives me 928 feet of number 4 bars. Now here's where we need to make the conversion because we price by pounds. We don't price by the number of feet. That's how RS means goes. That is often how you're going to be buying them from the rebar plant as well. So we're going to go in and get number 4 bars, and we got number 5 bars. This is actually an ASTM, and it really doesn't change from year to year. It's not something that you're going to have to worry about tomorrow going out and getting a new update. But I do mention that it's dated 2018 is when the last one I pulled off. And by the way, the previous one that I was looking at was dated, I think, through 2010. They hadn't changed. Right? The number 4 bar doesn't change from year to year generally. So we're going to find out that a number 4 bar is 0.668 pounds per foot. So if I know how many feet, I know how many pounds. Number 5, 1.043 pounds per foot. So if I know how many feet, I know how many pounds. Let's carry those over and figure out what the total weight of our bars are in tons. So we have number 5 bars. We got 1952 feet. We know what the weight is of those number 5 bars, 1.043 pounds per foot. So the total weight of number 5 rebars is 1952 times 1.043. Gives me 2,035.936 pounds. Now we need to convert that to tons. So we divide that by the 2,000. Remember, US uses 2,000 tons per pound. So we've got 1.017968 tons. Number 4 is the same drill. We're going to go in there with the 928. We're going to we got the 0.668 pounds per foot. We're going to multiply those 2 guys together and find out it's only 619 pounds, or 620 pounds. When we take that 619.904, divide it by 2,000, we're going to find out we only have 0.399252 tons. So now we know the tonnage of our rebar. Now we go out and price it. And so we're going to price this thing from this chart right here. And the first thing I got to warn you is that there's an ad down here you need to be aware of. Always keep a watch on those ads because this, if you remember our sizing factors, how do you size for very small or very large jobs? They give you a little sizing factor here. They say if the job is less than 10 tons, we're going to have to add 18%. And if the job is between 10 and 50 tons, you add another 9%. So that, by the way, is not cumulative. It's 9% if it's between 10 and 50, and if it's under 10, it's 18%. So whatever we find as a price up here, we need to make sure that we're grabbing the right the right add down there because we've got a very small job. This is a small job. So we're looking down here and we find out the reinforcement is sized or priced based upon the application. And that kind of makes sense because if we're doing a slab, that is completely different. I mean, we're just got long rebars just kind of laying there. Same thing with footings. Compared to a column and a beam where you've got lots, you might even have spirals going in a column or a beam. So you've got to figure out what you're doing with these things before you actually start pricing these things out. So let's go down. We're looking for, there's our footings right there. And you'll notice that they put it number 4s to number 7s. The reason that they're not so much worried about each individual bar because you already have priced them out per the ton. And of course, number 5 rebars are going to be higher in weight than number 4 rebars, so they're going to weigh more. So that basically is saying the cost difference between these guys is really related directly to the weight. It's not related to the size of the bar. And then the number 8 to number 18 it's a different grouping, but again, between that grouping, the weight is the primary determinant. It's not the individual sizes. So we're in the footings, number 4 and the number 7s. We're going to go across here. We're going to find out our daily output is 2 tons per day. So 2 tons per day. That tells me right now, roughly, since I know I've only got 1 ton and then 0.3 or something like that tons, that I'm going to be less than a day to put together the rebar. And it was 2.5 days for footing or formwork. All right. Then you look over here, and of course this is based upon the work crew. We got 4 rodmen for the work crew. We're going to use 16 hours for every ton, which kind of relates to the fact that, of course, we've got 2 tons per day. I mean, almost magically just kind of match right up. All right, let's take this thing right on across. We got this, let's make sure we got it highlighted. We're going to go across, we're going to find out $2,438 per ton. So that's my cost to put together the formwork, but we never forget, we've got to bring in this additive because we are in a situation where we're under 10 tons. So we're going to be multiplying that 2,438 by 18%. 1.18 is the factor. So we have a total of 1.32792, or I've added those two together. Now we've got the cost per ton. So my initial cost would be 2,438 times the tonnage. That's what it would be, but remember we've got the additive, so we're going to multiply times 1.18, and my price is $3,820. And then we also want to check the time. My reinforcement, if my daily output is 2 tons per day, and this is the number of tons I've got, I can tell you how many days it will be. I divide it into there and come up with 0.66396 days, which means it's going to be less than a day to put together the reinforcement. All right, we've got the formwork, we got the reinforcement. The last thing we need to do is the placement. And again, we're going to use placement as both the concrete cost and the actual installation cost. You could price these things separately. So what we're going to do is find the total cost with over and profit for placing the concrete with a direct chute. That means we're just going to drive up and dump it right there. If you had to do other things, if you had to do wheelbarrows, if you had to do a pump or something like that, you'd have to look for those adds because we're going to change the methodology. The unit measure is cubic yards of concrete. And so what we have is we have this little exterior rectangle section here. And it's just this little sliver. This is the same thing we did with our excavation homework, where we were trying to figure out these little slivers of excavation. So we want to know the volume of that. Now you could break this up any number of different ways. Like for example, you could cut the corners here and you've got these little 96-foot sections by 3 feet. Okay, you can do that. And you got 2 of those, and then you got the 142s on the end by 3 feet. So you can do it that way. Or you could divide it up over here, and now you got 136 sections over here by 3 feet. And over here, you've got the 102s to the exterior section by 3 feet. You can do it that way. Or you could do the centerline method, which is a little more complex because I'm going to have to take that 100 and subtract half of a foot from it on either side. So it'll be 99. 140 to subtract half a foot, that means 193, 139. And then I'm going to do that total perimeter and then multiply times 3. You can do it any number of different ways. So there's lots of different ways. This is the way I did it. Okay, so I did the 96 and then I did the 142. So again, if the geometry doesn't make sense, back up a couple of slides when I started this whole example and revisit why these dimensions are what they are. But the length of footing in each case, I've got 2 sections that are 96 feet, and because these are coming from outside edge to outside edge, they're 142 for each one of those sections. My total length of this footing is going to be 476. And I know it's 3 feet wide and 1 foot deep. So my volume is 3 times 1 times 4 is 476. It's 1428. 1428 divided by 27 cubic feet per cubic yard, and it will tell me that my total cubic yardage is 52.89. Now, I'll reiterate that I'm just kind of pressing on through this. We're in a video, so you have plenty of opportunity to stop and go back and refigure it out yourself. But the thing that usually causes about 10% of you the greatest amount of grief is not the reading the tables, not it's the quantifying. It's this geometry stuff. So pause, certainly pause, and make sure you capture the geometry before we go forward. So 52.89 cubic yards. So we're going to go into this table. This is a comprehensive cast-in-place concrete table. In RS means, again, there's pages of this, but there's also pages of just concrete alone. How much does it cost to get concrete and have it placed by chute, by pump, by whatever you're going to do? And then there's the installation, which is based upon the different types of applications and by concrete pump or chute or whatever. So you can actually price it separately, and that may make sense because the different applications have different things involved with them. But we're going to do the total. We're going to kind of shorten this for everybody. So we're going to go into the placement of the concrete. Concrete in place, we're in the section 0330, 53, cast in place. We've got an equipment pad. No, we're not going to do that. We got footings. Here we go. Spread. No, we're not spread. We're down to strip footings. Right there you go. And we're presuming it's 3,000 PSI concrete. If it was a different type of concrete, you would have to look in the ads or in a different section, break it out. And you want to see what the size of your footing is. In our case, we're using a 36 by 12. In other words, 3 feet wide, 1 foot deep. If it wasn't 36 by 12, what would you do? Would it be logical that you might have a 36 by 9? Yeah, it might be logical to have a 36 by 9. So you may have to do a little interpolation here depending upon how this goes out. In this particular case, because we got 2 dimensions, I wouldn't throw that at you on the homework, but just to make sure that you realize it may be logical to do a little interpolation off this chart, because you may have a footing that is 9 inches deep and 24 inches wide. You might have that. So just be prepared that you may want to do a little bit of modifications here. So we got the 36 by 12. We're going to go in there. We find out that the daily output is 70 cubic yards per day. We know we have 56, if I remember right, cubic yards. So we know we're going to get this footing done in a day. Like I said before, the formwork is always the most time consuming, and it generally is the most costly. The labor hours is going to be 1.37 hours of this crew, individuals in this crew, 1.37 hours per cubic yard. So the total price is $259 per cubic yard. We know we have 56.89 cubic yards. We know we have a total cost of $259 per cubic yard. Well, the total cost is, those two multiplied together, $13,698, which is coming close to my formwork. And that's simply because this is a very small pour, And so the form work and the cost of the concrete is actually moving together. I will tell you the form work generally is the most expensive. And then we've got how long will it take? We looked at that. We got 52.89 cubic yards. We have 70 per day. Well, we can divide that out and figure out what the number of days it would be. And so now we can take a look at the total price, and I've kind of captured them all here on the table. The formwork, $13,090, but a lengthy time to put that in there. The reinforcement, $3,820, and a very short time to place the reinforcement. And the mix and placement is there. Add them all up, we got 30,608.71. And a total of about 4 days to do this whole job. 4 days continuous, of course. You'll find that on a job site, this may take a week or two simply because getting the different crews in there. They're different crews. They're not the same people. All right, now we've got our price. That's our unadjusted price. I also want to emphasize that you need to be thinking about area cost factors. And in this case, the area cost factor needs to come out of the same book. We can't use the assembly's area cost factors. They don't work. We'll see that on this next chart. All right, let's take it to Wright-Patterson Air Force Base. This is a snapshot of, again, I've changed some of the numbers around, but this is exactly what the RS means depicts in its city cost indexes for the area cost factors for a unit price cost estimate. And you'll see over here that these unit price area cost factors or city cost indexes are based upon the section of the master format. So we're no longer in the uniformat sections, we're in the master format sections. And that's rather fortunate because our cost data came from the master format sections, right? So we're in concrete, so up here at 03, and you'll notice that it has the forms, the reinforcement, and the placement broken out separately. And that's common. There's some sections that are all one, like masonry is all one, but then there's other sections like for example, openings, where they break it out based upon the type of openings. And I've kind of shortened this chart a little bit for presentation, but nonetheless, you would need to go in there and make sure that you're following in which ones were right. Now, there is a total concrete value here. And that really captures all of those other specialty items and things that you might run into there. But since we have one for forms, we have one for reinforcement, and we have one for cast in place concrete, we're going to use those. So we're going to go across to Dayton, Ohio, right over here. We're going to use the total columns. We find out that the form work is 85.3% of the national average. We find out that the reinforcement is 86.9% of the national average. And we find that the cast in place concrete is 85.5. Very close to each other, but we'll use them separately. We'll use those numbers. So we take these numbers that we originally had, we multiply them times those averages, or those percentages, and then we come up with the new price, which in this case is 11,000, then it's 3,000, then another 11, close to 12,000, comes up to 26,197.77 for the cast in place concrete for that little building that we're building. So that's how you would adjust it for the area cost factor or the city cost indexes. Remember, the key foot stomp here is use the one that is associated with your cost data. Trying to go back to the UFC, trying to go back to the Assembly's Guide, it would fail you. You can pull a number out of there, but it's going to be the wrong number. Now, this is a good general cost. I want to emphasize that there's lots of things that you would be pricing, even with this one little simple task. There's things that you want to price in there. For example, vapor barriers, if that's something that you're going to be placing in there. Bonding agents, if you got two different pours or two different things that are coming together. Special admixtures, you might have air and trained mixes for a footing, especially because it might be freezing, it might experience freezing and thawing. Or there might be special hardeners, or I used to work with a contractor who put plasticizers or what hydrolyzers or whatever you would call those things in every mix. And the reason is because it saved them so much in labor that it just was, and in this area it's relatively inexpensive. It was pennies to save the amount of labor time. Those types of costs. Sealants. You might put some sort of sealant on the outside of those things or other type of joining material if you got joints. Expansion joints, and especially in buildings, you'll find an expansion joint. If you got a long building, you'll find an expansion joint in the middle of the building, and the footing has to carry that as well. Anchor bolts and things like that for if you've got a wall that's coming up. Remember that wall on that footing that we had? Well, there's probably anchor bolts that go up into that wall to tie that wall into the footing. And we didn't even price those. There's these other things that you get as far as the placement that's called chairs or hangers and things like that. What a chair is when that reinforcement's not laying on the ground. It's got to be up and embedded in the concrete. And so you put under there's these little plastic, you ever been in pizza boxes? And you got a pizza and there's that little plastic thing that keeps the lid from smashing on your pizza? It's something similar to that. You put these things on the ground, they stand on the ground, and they hold your reinforcement up. And basically that keeps your reinforcement properly placed in the concrete. So you'll see those types of things. And then there's anytime you change the methodology. If I'm doing an elevated slab, I have to pump it in there. I might have to hand mix it, depending upon the site or depending upon the availability of concrete. I might even do some precast material, which means casting it off-site and carrying it on-site. Special kinds of finishing that you might be doing at the end of it. So there's a number of different things that you're going to run into there. And you'll find these additives and deducts in the cost book. And don't ever forget when you're managing a project, and this is the emphasis here, schedule and cost are entwined. And concrete affects the schedule like you would not believe because you got a cure time. Most of your regular cure concrete is 28 days. There's no wanting it to go faster. A wing commander can direct it to go faster. It's just not going to go faster, all right? You can get high early concrete, and that's typically around the 7-day point where you can get some strength out of it. That high early concrete is going to cost you quite a bit of money. It's not just the cost of the concrete, although that is a price issue. It is also the cost of the placement because when you've got high early concrete, you've got to handle that stuff special. I mean, it can only be in the truck for a certain amount of time, and you got to put it in the ground. You got to get done handling it, and it takes some special handling. And so that high early concrete is not just a small deal. You got to look at it across the board. And then how do you maintain it during the cure period? Because if you're in freezing temperatures, you got to lay blankets on it. If you're in extremely hot temperatures, you got to worry about it cooking too hot, depending upon the volume of concrete you have in one place. You got watering of it, making sure it doesn't dry out, sealing it, and all kinds of different types of agents. Again, and if there's impacts to the crews and schedules because you have to wait for that amount of time before you do the next step or whatever you're going to place on top of there. So again, this is not a scheduling course. We're not dealing with how you come up with a schedule, but I want to emphasize that the schedules and costs go hand in hand. And this whole dynamic can affect your costs because there may be time in the schedule where the contractor just has to walk away from the site and say, we're waiting on the concrete. In which case, you're paying money for no work. So think through that. So this is a practice problem I'll give you on your own. I'll put, of course, the answers in on the site so you can actually see how it was supposed to occur. But basically, we're going to do this. Remember that visitor center? Well, there's also out there a little guardhouse. And if you look through your visitor center drawings, you'll find the guardhouse. And that little guardhouse is just a little small building. It's got a little demi-whittle right here, okay? But we can look at that. And what we're going to do is we're going to place some spread footings under these 4 columns. So you got 4 columns, and we're just going to place spread footings. We got 3 by 3 by 12 spread footings. We're going to use forms. We're going to assume these types of forms. Forms are going to be in place with wood, one use, and only the sides require form work. So we're not going to form the undersides. We're not going to form the top. We're just going to form the sides of the footings. So you're just basically going to measure 3 by 3 by 3 by 3. So I might have already given you the length of footing all the way around that guy. And then we're going to use regular cast in place 3,000 PSI concrete, and we're going to use number 6 rebar every 6 inches. So it's basically 6 inches in, that's 6, that's 1 foot, 6, 2 foot, 6, 3 foot. So you can count how many rebars you're going to have. And again, we're going to go all the way to the length. We're not going to worry about cover requirements. So the civils out there are probably having heart palpitations. I understand, okay? But we're going to price it without the cover requirements. Obviously in design, you're going to worry about that. But in the pricing, we're not going to do that. So you can count how many rebars and the length of the rebars and everything. It's going to go in both directions. So do this project on your own, and then do it on your own, and then look at the answers. Don't just kind of leaf through the answers and say, I get it. Because if you haven't done it on your own, then you haven't made the tripping hazards that you haven't yet worked through. That will prepare you for the homework. And again, the form work, we've got the same table as we had before, so you're going to use this. Only obviously you're not going to use the continuous. You're going to use the same weights for the rebar, so I gave you a clean chart here without any circles on it so that you can pick that out. And then you're going to use the same pricing for the reinforcement bars, obviously, and then the same cast in place. So I gave you all the tables in the slides here that you're going to use. So that's that little exercise. Hopefully you go off and do it. Now let me introduce the homework. We've got the same building here, same building. Now we're going to place the slab. All right, so the key thing remember about the slab, or as far as the geometrics, we got that little stem wall that's going to be, in this case, CMU, so we're not going to do cast in place concrete for that. But that goes 12 inches in. All right, so the same thing we talked about before, the outside edge of the building is where the 100 and 140 goes to. And then the slab starts 12 inches in. Remember, slabs cannot be tied into your structural members. They have to be something separate. So we're going to place that slab. There's no formwork, because essentially what I'm going to presume is I'm going to put in some sort of agent or maybe a vapor barrier or something like that, and I'm going to use this outside stem wall as the form. So I do not have to pay for formwork. So I took, of the 3 things I've taught you, I took one of them away. You no longer have to figure out what the formwork is, okay? We've got the reinforcement. We're going to do welded wire fabric. I'm going to take a look at the welded wire fabric, but it's just another chart. We already saw reinforcement on the previous chart. Now we're going to take a look at welded wire fabric, and it's just another chart. You're going to use that on the homework. And by the way, the size and shape will vary with your homework version, because everybody's got a little bit different one. So you might have a 4x4 or 6x6 or something like that. And then the slab depth will also vary with homework. So it might be 4 inches, might be 6 inches, might be 5 inches, whatever it is. It's going to be whatever you have. We're going to presume that the welded wire fabric is going to go the entire dimension. Again, no cover requirements. It's just going to go to the outside edge. So what charts do you need? I've got the welded wire fabric here. So you're going to see all the different types of fabric, and I told you how to decode this. You don't have to decode it to solve the problems in the homework, but essentially, you know, a 6x6 grid means it's 6 inches by 6 inches squares, and they're going to be 1.4 wire. That's the number of wire that they're using. So we got the different options for that, for those types of wires, and then we got the 4x4 grids as well. Now, interestingly, you can also find out what the weights of these wires are per 100 square feet. That's what CFS is. It's 100 square feet. And why that might be important, you really don't need to know it in order to price out that welded wire fabric for the slab, but there's a couple of ads I want to bring out to your attention. If you have galvanized wire, and some of you will have galvanized wire, you're going to need to add a price per pound. And you might say, well, Tom, I know the square footage of my welded wire fabric because we're going to price it based upon 100 square feet. How do I know how many pounds there are? Right here. So if I have 1,000 square feet, I know that there is 30 pounds per 100 square feet, then I know that I have 300 pounds. 1,000 divided by 100 is 10 times 30 pounds. I come up with 300 pounds. So the key thing is if you've got either galvanized or if you've got epoxy coated wire and you have one or the other, then you need to make sure that you remember to put this add-on based upon the number of pounds of wire that you're using. And you can find out the number of pounds from the wire that you have up over here, which is based upon the 100 square feet. And what is the 100 square feet? The dimensions of the slab. So I'm kind of decoding your homework for you, okay? Hopefully that makes sense. Now the cast in place concrete, it's the same chart we've seen before. Just make sure that you're pulling it off this one in case there's any typos and then the other ones or whatever. This is the one that I will be using to evaluate the homework. And you pick out the right appropriate line item. I'm not going to point it out for you. Okay, pick the right line item based upon the thickness of the slab, and that will price out your slab. So you got to come up with the reinforcement, which is welded wire mesh, and then you got to come up with the slab cost. And that's unit price estimating the concrete. I didn't, again, the folks who are not civil, who are going, oh, I didn't know I was going to have to become a civil to do this. Well, we didn't really dive into all this stuff in concrete. I didn't talk about admixtures and the fabrics and other kinds of mixes and all the other kind of strengths. And we didn't pull up row. All right, the concrete guys out there are probably right now having starting to salivate. We didn't talk about all that other kind of stuff. We just talked about how you go to the tables with what you know, and the primary thing was the geometrics of the concrete, right? Trying to figure out the geometries and how you price that out based upon that. In the same vein, we can go through the rest of the civil sections. We can go through the rest of all of the sections and look at each one, and once we know each one of these little different dimensions, we'd be able to then price them all out. So having a design, we're now able to come up with the costs of the quantities of concrete and concrete requirements, and then therefore come up with a price. So with that, press on with the concrete homework. I know there's other elements to the concrete homework than just this lesson, but I wanted you're now prepared to do that, and we will come back and start talking about the other disciplines as we press forward.